Hey class, Adam Ward here. I want to talk to you this evening about modeling heat. You've got two video lectures to watch about heat. This is the first one. This is the fundamentals of how we'll deal with heat in our simulations. This goes along with lecture 30 in your Chopra textbook. And so just like we don't really model concentration, we model mass expressed as concentration, we don't really model temperature either. We move heat through our model, but we express it as the resultant temperature. So let me try and draw that comparison a little more clearly. We're used to modeling masses, but expressing them as concentrations. And of course, we know that concentration is mass per unit volume. There's a nice parallel to what's going to go on with our heat balances in this class. We're actually interested in heat, but we're much more accustomed to expressing that as temperature. So what's temperature? Temperature is basically a concentration of heat. So on the top you've got heat, and then on the bottom you've got the density times volume, so the total mass of an object or mass of water in our control volume, for example. And then you've got a C sub P down there, which is specific heat. And I want to take just a moment to explore specific heat a little bit more. So this is the equation that was in the bottom right on that previous slide. Specific heat, this is defined as the amount of heat it takes to raise a unit mass by 1 degree Celsius. On the top is the actual term in heat. Heat units could be calories, joules, BTUs, which are British thermal units. Let's take a look at a few different materials on the next slide and see what this is going to look like. Typical units for specific heat might be joules per kilogram degree C, calories per gram per degree C, and so forth. So you've got a heat on the top, you've got a per mass per degree C on the bottom. Let's take a look at some typical materials here. And so I'll show you the density and specific heat. So first, cast iron. If you've cooked with a cast iron pan, for example, or you've got an old furnace that might have a cast iron boiler and a steam or hot water furnace, one, incredibly heavy, right? Density is very large, and specific heat is very small. Right? Now that's great for a pan because it heats up quickly. You can heat up a cast iron pan relatively rapidly because of that specific heat capacity, or that specific heat, excuse me. You consider brick. They weigh less per unit volume, so less dense, and their specific heat is higher. It takes more heat to warm that brick than the metal that would be around it. Right? So think of your fireplace with a fireplace grate in there. Right? It's typically got a brick surround that helps absorb and dissipate that heat. Let's take a look at water. Density, just about 1,000 kilograms per cubic meter. And notice that specific heat is incredibly high, 4,182 joules per kilogram per degree C. That has a lot of side benefits to you and I as we live on this planet because we've got such large masses in the ocean that water is actually able to help stabilize otherwise fluctuating temperatures. So water is able to hold quite a lot of heat, and you can change the heat balance pretty dramatically without having a major effect on water temperatures. Finally, dry air, of course, not very dense at all, and a relatively high specific heat. So it takes a decent amount of heat to actually transfer or change the temperature of air. So those just to get your head around sort of what is density, what is specific heat, and the idea that they don't have to go together. So things that are dense are not necessarily good conductors of heat. Things that are light are not necessarily good conductors of heat either. Okay, so if we think about a simple CSTR with an inflow and outflow and possibly some other terms, I just wrote exchange here generically. First, let's take a look in red at what we're accustomed to. The time rate of change of mass in the system. That's what we've written here. We did this back in lecture 3. And then we typically make this simplification, and we pulled that volume out front. We said, well, let's assume the volume that we're going to deal with is constant. And that's how we got into the world of modeling concentrations instead of masses, which would be volume times concentration. We'd have an inflow and outflow, and I just wrote ... right? We could have settling terms, first order reaction rates, all kinds of things. That's what we've been accustomed to this semester. For modeling heat, we're going to do something very similar. So what I've written here in blue is an equation for the time rate of change of heat. And so you'll notice that just like mass is volume times concentration, heat is temperature times total mass times specific heat. So that term in the parentheses is actually describing to us how much heat is there in the volume that we're studying. Just like above, we can take some constants, density, volume, specific heat, and pull those out front. And then let's look at the rest of the terms we've got. Inflows, so Q in, that looks just like we had before. And now instead of concentration in, we're actually trying to get at heat in. So density times specific heat times temperature in. Very similar equation, or term, excuse me, for the outflow. And at the moment, we're just going to call any exchange with this sort of generic term, A sub S, meaning the surface area, times J. And so that J is a heat flux. Yeah, heat flux across the surface. And so we know that that's got to have units of heat, the thing that's moving that we're interested in, per area per time. And so this short snippet of lecture should have you comfortable with the units of heat and temperature, how heat and temperature are related to one another, how you could formulate a heat balance for a CSTR, and the idea that there can be exchanges of heat across the surface of our CSTR, our river, our stream, whatever it is that we're going to model. In part 2 of these video lectures, we'll take a look at this term and figure out how is it that we can estimate that heat flux. What are the sources? What are the sinks? How does our stream interact with the atmosphere to get the temperature that it has? So stay tuned for that, and thanks for sticking with me, class.